Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be discussing standard reduction potentials and what we call E0 or E0, depending on your pronunciation. So, going for an overview, we're going to talk about how we can determine the voltage of a galvanic cell. So think about being able to predict how much electrical energy that a galvanic cell is going to produce. Theoretically, and so then we can compare it to practically. We're going to become familiar with the standard hydrogen electrode as a reference cell that we can use to measure the voltage of all the different half cells we might come across, and to help us produce a table of standard reduction potentials. We're going to talk about why we need standard conditions, and then introduce what we call the E0 or E0, and how that connects to oxidation and reduction, spontaneous reactions. So determining the voltage of a galvanic cell. Okay, so it's important that we can actually make a prediction of how much voltage we're going to get by combining different half cells together in a galvanic cell. You think about it in terms of battery design. If you want to be able to get the most electrical energy out of a rechargeable battery for a laptop, then you're going to want to be able to work out what combination is going to give you the most voltage. Okay, and then be able to, you can plan accordingly. And so we would need a way to determine that theoretically, rather than just building a whole bunch of stuff. Okay, so we can actually measure the voltage that different things are going to give off, the potential difference across the two electrodes of the cell, which is called the electromotive force, or EMF. Okay, so how much force is involved in pushing those electrons through a circuit, and which is essentially then the maximum voltage that that cell can deliver. It can't deliver higher than that. It can deliver lower if the conditions aren't right or if it's not set up correctly, but the idea is that that's kind of the maximum value. But we want to be able to actually work out what that maximum is. So in order, then we set up a whole bunch of different half cells and we connect them up to one particular electrode, which we have set to be hydrogen. Okay, we set up the standard hydrogen electrode. So this is kind of how it's set up, and I'll show you a diagram in a moment. So we have a piece of platinum metal, which is our electrode, immersed in a 1.000 mole per litre solution of hydrogen ions in the form of hydrochloric acid, a strong acid. And we bubble hydrogen gas through at exactly 100.0 kilopascals of pressure. Okay, so what we have then is that then the half cell is the hydrogen ions and the hydrogen gas reacting together, and the platinum is a facilitator of the electron transfer rather than participating in the reaction itself, because platinum is a very not active metal, a low active metal. So what we have here over on the left is our the left is our hydrogen half cell. Okay, so we're bubbling our hydrogen gas in, we've got a solution of hydrogen ions in the water, and we have a piece of platinum, which is what's going to allow electrons to transfer up and out and across to the other half, which in this case is a zinc half cell. Okay, so we're using our standard hydrogen electrode, connecting up all sorts of half cells, measuring the cell voltage, so that we can actually express some relative values. And these values we call standard reduction potentials. So they are a standard electrical potential, or kind of values that are measured relative to our standard hydrogen electrode. Okay, so we connect it up, we measure the voltage, and we also include its sign. So we look at whether that helps us to work out which direction that electromotive force is pushing in. Is it pushing towards the hydrogen electrode or away from it? And we give it the symbol of a capital E, so the standard that standard potential. Okay, so the electromotive forces of such cells, so when we connect them up this way, we call them standard reduction potentials, or standard potentials you might see on a data sheet. Now, what we want to talk about is, okay, why do we need some standard conditions? Okay, because the reality is that we want to make sure that our measurements are consistent and reliable, and in order to do that we need to establish certain criteria for how these measurements are to be conducted. Okay, so this is not bucket chemistry here. Okay, so we set up what we call the standard state. So when we've got the ion that's associated with the electrode, it's exactly 1.000 mole per litre. Any gas is at exactly 100.0 kilopascals. So it's important that those conditions are adhered to so that we can be confident in the voltage we're going to produce. Because if we change either of those factors, that then it's going to alter things. And it's going to alter the measurements that we can make. Okay, so that when we've measured under these conditions, we give it the symbol of E and a naught, or kind of a 0. Now this is kind of like a Greek sort of letter phi, because it's kind of, yeah, where it's kind of part standard, but it's in our context, it's meaning the same thing. So these standard potentials measuring under standard conditions. Okay, so this is kind of an extract of the sort of thing that you would come across. So some standard potentials that are measured. Okay, so where we're expressing, say, for each of these processes that we've measured, connected up those half cells and measured the voltages. Okay, so hydrogen on the table comes out at 0. We can see that some numbers are very negative, others are very positive, and kind of from all the spectrum in between. And then what we can see is that the magnitude of the number and its sign, so how big it is and whether it's positive or negative, is useful information for us in terms of oxidation and reduction. So the idea is that standard reduction potential gives us an indication of how likely it is that that substance will undergo reduction. So if we have a number that is more positive, that it will prefer to be reduced. It will have the tendency to reduce. A more negative or less positive cell standard reduction potential will prefer to be oxidized, is less likely to reduce. Because the idea is, remember, we're always connecting up two half cells together, so we're always looking at one thing compared to another thing. Saying if I compare A and B, or if I combine A and B together in a galvanic cell, how much voltage am I going to produce? And this way you can predict, well, which process is each thing going to do. So we're always expressing these values for the reduction reaction. Okay, which is why we're calling them standard reduction potentials. We know that it's not always saying that all processes are always going to be reductions, because we know that can't work, but that we're reporting these values all in the same way for consistency. And then we can take those and we can work with them to calculate voltages, and we'll look at that in the next video. Okay, but it also not only helps us to work out whether oxidation or reduction is going to occur, but also whether a particular reaction, even if, once we've worked that out, is going to be spontaneous or happen all on its own. Okay, so for a redox reaction to be spontaneous, we need two main conditions. The first one is that we need both a species that can be reduced and one that can be oxidized, so that we get both processes. And here's another crucial factor. The E0 of the species being reduced must be greater or more positive than the E0 of the species being oxidized. Okay, so if we're trying to get a reduction of the one that is less positive or more negative, then we end up, so that it doesn't tick that second box, then what happens is that those reactions can still work, but we must apply an external voltage. We must plug them into something else that is able to make that reaction occur. They will not spontaneously do that. And just by connecting up the cell in the right way, you need to put in an external voltage. Okay, and we look at this in terms of what we call electrolytic cells, the opposite of galvanic cells, or where we're using electricity to force non-spontaneous reactions to happen in situations where that might be exactly what we're after. So electroplating metals is one classic example, where we're using that energy because that's what we need in that particular situation, because it won't spontaneously happen. Okay, so we've looked at why we want to determine the voltage of a particular galvanic cell. We looked at how we can actually establish a reference point of the standard hydrogen electrode and compare all other half cells to that. Once we've measured the different cells that we produce, we can come up with a table of standard reduction potentials, and those values are what we then take and we can use to calculate cell voltages. We looked at why we need standard conditions for consistency and reliability, and how those E0 values can also tell us about whether oxidation or reduction is going to occur. And then whether a reaction is going to be spontaneous or not. All right, thanks very much for watching. Bye for now.